This is lesson 7 on fluid mechanics in medicine, and the topic is the Bernoulli equation. The learning objective is to be familiar with some of the diverse applications of the Bernoulli equation and to be aware of the Venturi effect. In the last lesson on the continuity equation, we started with a fluid conduit of variable cross-sectional area in which some non-compressible liquid was traveling left to right. And we looked at how the product of the cross-sectional area and the velocity in one segment must be equal to the product of the cross-sectional area and the velocity in another segment. For the Bernoulli equation, we're not directly interested in the cross-sectional area in each segment anymore, but rather the velocities, the pressure, and the height of the fluid above some arbitrary zero level. In the interest of time, I'll spare you its derivation and just give the Bernoulli equation to you. The pressure at point 1 plus 1/2 the fluid density times the velocity at point 1 squared plus the density times little g times the height at point 1 must equal the sum of those same values at point 2. Or another conceptually identical version states that this sum is a constant. This equation may look a little unwieldy until you realize that just as the continuity equation is nothing more than the law of conservation of mass as applied to fluids, the Bernoulli equation is the law of conservation of mechanical energy applied to fluids. This term is the potential energy density of the fluid. This term is the kinetic energy density of the fluid. And this term is something called pressure energy density. Don't worry if the term pressure energy is totally unfamiliar to you. Just know that as a liquid travels through a conduit, these various energies trade off at different points, but their sum is always the same. For the rest of the video, I'll go through two rather different examples of how to apply the Bernoulli equation. First, imagine we have a bucket on top of a marble block. If a hole is drilled at the bottom of a full bucket of water, whose height is h, what velocity will the water have when it initially exits the hole? This problem may seem unexpected at first, since a bucket of seemingly stationary water looks quite different than the conduit I referred to a second ago. However, the water in the bucket is not stationary after all, and the bucket is just an unusually shaped conduit. Let's start by writing out the full Bernoulli equation. Next, we need to define a point 1 and a point 2. One of these will obviously be the exit hole, and the other should be a location where we know the most information. In this case, it's the top of the barrel at the water line. So there are points 1 and 2, which makes this velocity v2. So how can we substitute in for the missing variables? First, the pressure at point 1 is atmospheric pressure. What is the velocity at point 1? By the continuity equation, the velocity times cross-sectional area at point 1 must equal the velocity times cross-sectional area at point 2. However, if we assume that the cross-sectional area of the entire barrel is much larger than that of the hole, the velocity at point 1, that is how fast the water line is moving down, is very small and for practical purposes can be assumed to be 0. The value of y1 is the height of point 1 above some arbitrary level. We can make that arbitrary level anything, but let's make it the top of the marble block. So y1 becomes h. Next we have p2. This may or may not seem intuitive, but if point 2 is located just at the lip of the exit hole, the water here is also exposed to atmospheric pressure. So p2 is also p atmosphere. v2 is of course what we are solving for, and y2, or the height of point 2 above the top of the marble block, is 0. So p atmosphere cancels out, and this term is 0, as is this one. This gives us density times little g times h equals 1/2 density times v2 squared. Densities cancel, and solving for v2, we find that it is equal to the square root of 2 times little g times h. There are a number of fascinating things about this rather elegant solution. First, the velocity of the fluid coming out is independent of its density. Whether it's water or mercury, the velocity will be the same. Next, the width of the barrel and the width of the hole are both irrelevant, provided that the barrel is many times larger than the hole. Finally, and most interestingly, This is the same velocity that an object or fluid would have as it passed point 2 if dropped from an h and allowed to fall straight down under the influence of just gravity. This is historical trivia, but this solution is called Torricelli's theorem. Torricelli is the 17th century Italian physicist who invented the barometer and for whom the unit of torr is named after. Let's look at another application of the Bernoulli equation, one that's a bit more complicated. Here's a schematic of an interesting contraption called a Venturi meter. It consists of a horizontal tube of two different widths, where a vertical tube is attached to both the wide section and narrow section. A fluid moves along its length. You've probably already noticed something interesting. The height of the vertical columns of fluid are not equal. This might seem to be a violation of the principle discussed in the lesson on hydrostatics, that fluids always seek their own level, but that only strictly applies to stationary fluids. This is an example of the Venturi effect in which the pressure in a fluid moving through a conduit is decreased when the fluid flows through a constricted section. The term Venturi effect is also occasionally used more broadly for a variety of related phenomenon, particularly in medicine. How could we analyze this situation quantitatively? Suppose we can measure the height difference between the two columns, which we will call h. Given only a1, a2, and h, what is v1 and v2? I can imagine this seeming like a profoundly difficult problem, but I guarantee you that we have already covered all of the tools necessary to solve it within this video series. So let's start with the complete Bernoulli equation. We see that although the pressures, that is P1 and P2, are neither given to us nor requested as part of the solution, we'll still need to include them along the way. The first simplifying step is to realize that the vertical height of the two sections is the same, so these terms cancel out. With a little rearrangement of the remaining terms, we are left with P1 minus P2 equals 1/2 the density velocity 2 squared minus half density velocity 1 squared. Factoring out the 1/2 in density gives us this, which is looking more manageable. But where do we go from here? The first trick is to realize that in order to get rid of the unknown P1 and P2, we will need to use our knowledge of hydrostatics, and we'll need to define, at least temporarily, a different height, that is the height from the center of the main horizontal conduit to the top of the lower of the two vertical fluid columns. I'm going to call this h prime. How does defining h prime help? We know from hydrostatics that the hydrostatic pressure is density times little g times the height of the overlying fluid. So P1 is equal to density times little g times the sum of h and h prime. The same rationale allows us to state that P2 is equal to density times little g times h prime. And a simple but nevertheless cool algebraic trick allows us to simply subtract one equation from the other, giving us this. P1 minus P2 equals density times g times h. And we can substitute that right in here. The next major trick to achieving the solution to this problem is to remember the continuity equation. A1 times V1 equals A2 times V2. Solve for V2 and substitute that in here. And with these two substitutions, we are left with this. Density cancels, and everything that is left is either given or is what we are solving for. At this point, we leave physics behind and concentrate just on the algebra. Multiply both sides of the equation by 2, factor out the v1 squared, and solve for v1. To arrive at an expression for v2, substitute all of this back into the continuity equation. This answer might initially look ugly and cumbersome, but I actually find it kind of awesome that the velocity of fluid moving through this tube can be determined from the ratio of the cross-sectional areas and the difference in column height. That's it for Bernoulli and Venturi in physics. The next video will cover 2 examples of using these principles in medicine.